When we think of the end, we expect chaos. Earthquakes cracking roads, explosions destroying blocks, volcanoes burying cities. Hollywood and history teach us catastrophe is loud, sudden, and visible. We expect a warning, but there is a different kind of disaster unfolding right now, one that offers no such courtesy. It is happening in the American Southwest, specifically in the sun-bleached expanse of Arizona. It is a catastrophe that moves with the silence of a shadow and the slowness of a glacier, but its destructive power is rivaling the most violent events in geological history. The state of Arizona is disappearing. It is not being swallowed by the sea or blown away by the wind. It is being sucked into the earth itself. Large swaths of the landscape are sinking, losing elevation year after year, dropping silently into the voids we have created beneath them. This phenomenon is reshaping the topography of the state, cracking the foundations of modern infrastructure, and posing a question that few are ready to answer. What happens when the ground we stand on simply gives up? To understand why this is happening, we have to strip away the asphalt of the highways and the concrete of the strip malls, and look at what lies beneath the desert floor. There is a fundamental misconception that Arizona sits on solid rock, a continental shelf of granite and basalt that is immovable. The reality is far more fragile. The geology of the region is more like a layer cake, a complex stratification of sand, clay, silt, and gravel that has been deposited over millions of years of erosion. In its natural state, this sediment is stable, capable of supporting the weight of mountains and cities alike. But that stability relies on a crucial, hidden ingredient. Think of the ground beneath Phoenix or Tucson not as a block of stone, but as a giant, saturated kitchen sponge. When a sponge is full of water, it is plump, expanded, and resilient. The water trapped inside the pores of the sponge exerts outward pressure, holding the fibers apart and maintaining the sponge's structural integrity. This is exactly how the aquifers beneath Arizona function. The water, ancient, fossilized water that has trickled down over millennia, is not just sitting in a tank. It is occupying the microscopic spaces between grains of sand and clay. It is a hydraulic support system, physically holding the earth up, pushing back against the crushing weight of the soil above it. But for the last century, humanity has inserted a straw into this sponge. We have pumped this water out to irrigate cotton fields in the desert, to fill the swimming pools of sprawling suburbs, and to hydrate a population that has grown exponentially in an environment that was never meant to support it. The problem is one of simple math and brutal physics. We are extracting this water faster than nature can replenish it. In many cases, we are mining water that fell as rain 10,000 years ago, during the last ice age. When you remove that water, the hydraulic support vanishes. The hydrostatic pressure drops to zero. The consequences are immediate and terrifyingly permanent. Without the water to push them apart, the grains of dirt and clay have no choice but to surrender to gravity. They are squished together by the immense weight of the world above them. The air pockets collapse. The geological matrix compacts. And when that happens, the ground surface has nowhere to go but down. This is the mechanism of land subsidence. It is the earth imploding in slow motion. The terrifying reality of this process is that it is irreversible. Going back to the sponge analogy, once a sponge dries out, it shrinks, but you can always add water to fluff it back up. The earth does not work that way. When these deep alluvial layers collapse, they behave less like a sponge and more like a crushed aluminum soda can. You can crush a can in a second, flattening it into a disc, but you cannot simply blow air into it and expect it to pop back into its original pristine shape. The structure is ruined, the metal is fatigued, the integrity is gone. Once those underground layers of clay and silt are compressed, they stay compressed forever. The storage capacity of the aquifer is permanently destroyed. Even if the climate were to change tomorrow, even if it rained for 40 days and 40 nights, and the desert bloomed into a rainforest, the ground would not rise back up. It cannot hold the water anymore. We have effectively destroyed the vessel. This is a one-way trip into the earth. It does not matter if the water was pumped out by a farmer in 1950 or a golf course in 2024. The result is a cumulative compounding debt that the land is now calling in. How do we even detect a disaster that moves inches at a time? From the surface, subsidence is invisible to the naked human eye. It is the perfect stealth predator. You do not wake up one morning to find your house sits 5 feet lower than your neighbor's. The horizon looks the same. The mountains appear unchanged. The drop is uniform across massive basins, meaning everything goes down together. The roads, the houses, the power lines, and the people. It is like being in an elevator that is moving so smoothly you do not realize you are descending until the doors open on a different floor. To truly see the scale of the collapse, scientists have had to leave the planet. They have turned to the vantage point of space, utilizing a technology known as interferometric synthetic aperture radar, or INSAR. These are super precise scanners orbiting hundreds of miles above our heads. They bounce radar signals off the surface of the Earth and measure the return time with agonizing precision. They can detect changes in ground elevation that are thinner than a United States nickel. When scientists pointed these satellites at Arizona and tracked the data over several years, the results were not just concerning, they were alarming. They produced maps that looked like heat signatures of a fever. Large areas of the state were glowing red, indicating steady, relentless downward motion. Some places were dropping by inches every single year. In certain agricultural regions, the total drop added up to several feet in just a short span of time. Entire basins were sinking. What made this data even more chilling was the realization that the sinking did not stop during the wetter years. There was a hope that perhaps a heavy monsoon season or a wet winter would pause the process, allowing the aquifers to breathe. But the satellites told a different story. Even when rainfall increased, even when the reservoirs filled slightly, the land kept sinking. In some places, the process actually sped up. This told the geologists that the ground was no longer reacting to short-term weather patterns. It was responding to decades of pressure building underground. The momentum of the collapse was now self-sustaining. The Earth was settling into its new, compacted reality, and nothing we did on the surface seemed to be able to arrest the fall. While the sinking itself is silent, the physical manifestation of the stress is violent. The land does not sink evenly. The geology of Arizona is not uniform. There are ridges of bedrock, varying depths of sediment, and different soil compositions. One spot might drop 6 inches in a year, while a spot 100 yards away only drops 1. This differential creates unbearable tension in the crust. The surface tries to stretch to accommodate the changing geometry, but rock and asphalt are not elastic. Eventually, the tension exceeds the strength of the material, and the earth snaps. These are not the small sidewalk cracks you step over on your way to the grocery store. These are known as earth fissures. They are jagged, gaping wounds in the desert floor that can run for miles. They rip open without warning, creating trenches up to 15 feet wide and tens of feet deep. They are wide enough to swallow livestock, tear cars apart, and split paved highways down the center. They are the physical scars of our thirst, appearing across the landscape like claw marks. Infrastructure absolutely hates this phenomenon. Engineers design roads, bridges, and canals based on the assumption that the ground is a constant variable. When the ground becomes a variable, the math falls apart. Roads bend, twist, and buckle as the earth beneath them retreats. Underground utility lines, gas, water, electric, are yanked out of alignment or sheared completely, creating hazards that can lead to those loud disasters we mentioned earlier. Perhaps most ironically, the canals that were built to bring water to these parched regions are imperiled by the very problem they helped create. These canals depend on gravity to move water. They require a gentle, steady slope. When the ground sinks unevenly, the slope changes. The water stops flowing. The lifeline is severed by the gravity it relies upon. Even private homes are not immune. A house built on a fissure zone is a ticking time bomb. Foundations crack, floors tilt, and doors refuse to close as the frame of the building twists. Walls develop long, jagged fractures that look like lightning bolts, frozen in drywall. And for those living in rural areas, the impact hits their water source directly. As the ground compacts, it crushes the rock layers like a vice. This closes off the pathways that water uses to flow into wells. A well that has provided water for 3 generations can suddenly turn into a dry hole, not just because the water level dropped, but because the rock itself has been sealed shut by the crushing weight of the earth. By pumping too much, we are quite literally breaking the pump. This is not a localized problem. These issues spread across entire basins. The damage can manifest miles away from where the pumping is actually occurring, making it a legal and logistical nightmare to assign blame. By the time the surface damage becomes obvious, by the time the fissure opens up in your backyard, the underground changes that caused it are already locked in. The damage is done before the symptom appears. The real challenge isn't fixing the crack you can see. It's dealing with the millions of tons of earth that are slowly shifting beneath it. So, can this be stopped? Is there a way to reverse the process and inflate the ground back to its original level? The harsh scientific reality is that there's no undo button. There is no technology on Earth that can inject enough pressure underground to lift a city back up. Once that pore space is lost, it is lost for geological time. The best we can hope to do is step on the brakes. We cannot fix the past, but we might be able to prevent the future from collapsing further. Arizona has attempted to mitigate this through massive engineering projects and strict legislation. One approach is artificial recharge. The state has built a colossal network of aqueducts, known as the Central Arizona Project, a canal system that stretches more than 330 miles, carrying water from the Colorado River deep into the desert heartland. When there is excess water, they don't just use it, they dump massive amounts of it into giant empty fields called recharge basins. These look like dry lakes that are suddenly flooded. The goal is to let gravity do the work, allowing the water to seep back down through the soil and repressurize the aquifers. But we must be clear about what this achieves. It is not fixing the crushed sponge. It is simply trying to stop the crushing from continuing. It is like loosening a vice grip. The object in the vice is already deformed, but at least you aren't squeezing it any tighter. You don't get the space back, but you can stabilize the patient. The other approach is political, and it is far more difficult. Arizona has drawn hard lines on the map called active management areas. Inside these zones, which include major population centers like Phoenix and Tucson, groundwater use is tightly limited. You cannot just drill a well and pump non-stop. The philosophy is to balance the checkbook to only take out what you can prove you are putting back in. In the areas where these rules were implemented early, the sinking is actually slowed. It proves that human behavior is the driver, and changing that behavior can have an effect. But in the rural parts of the state, where agriculture is king and the rules are looser, the ground has kept dropping, driven by the insatiable demand of industrial farming in a desert that was never meant to grow thirsty crops like alfalfa. It is important to understand that Arizona is not an anomaly. It is simply the latest member of a terrifying global club, the sinking cities. If you look at the Central Valley of California, you see the world champion of deflation. It is the engine of American agriculture, but the cost has been astronomical. Farmers there have been pumping water so aggressively for so long that in some spots the land has dropped by nearly 30 feet. Utility poles that were once flush with the ground now have markers high above human heads showing where the earth used to be in 1950. Gravity-fed irrigation canals there are confused, trying to push water uphill because the destination has sunk lower than the source. Or look at Mexico City, perhaps the most tragic example of all. The problem there goes back hundreds of years to the Aztecs and the Spanish. The city was built on top of an ancient drained lake bed. As the modern city grew and pumped out the aquifer to support millions of people, the clay soils began to dry and compress. In some neighborhoods, the sinking is measured in feet per year, not inches. Historic cathedrals buckle. The sewer system runs backwards, and streets have to be repaved endlessly, layer upon layer, just to keep them usable. The city is drowning in the earth. From coastal towns in Virginia to the rice paddies of Southeast Asia, the ground is getting tired of holding us up. Arizona is just proving how sneaky this disaster can be. It quietly reshapes the world while we are busy looking at our phones, distracted by the noise of modern life. It forces us to confront a reality we try to ignore, that the resources we depend on are finite, and the earth we build on is not inert. We treat the ground as a stage, a static platform upon which the drama of human history plays out. We assume the stage will always be there, unmoving and supportive, but the stage is actually a raft floating on a sea of water and rock. And we are slowly deflating the raft. When we wonder how huge chunks of the planet can sink this quietly without anyone noticing, we have to look at our own perception of time. We live in minutes and hours. The Earth lives in eons. To the Earth, this collapse is instantaneous. To us, it is slow enough to ignore until the walls crack. It really makes you rethink the phrase, solid ground. There is no such thing. There is only the temporary balance of forces, gravity pushing down, water pushing up. When we disrupt that balance, we invite chaos. Maybe the ground floor will become a basement in 30 years. Maybe the map of Arizona will look fundamentally different in a century, not because of borders, but because of elevation. This is the earth sending us a bill. For decades, we have treated water as a free commodity, something to be used and discarded without thought. But the accounting of geology is strict. Every gallon pumped out has a cost in structural support. We are paying that debt now, not in dollars, but in the very stability of our civilization. The fissures opening in the desert are not just geological curiosities, they are receipts. As we continue to expand into these arid environments, driving deeper wells and demanding more from the dry earth, we are engaged in a race against the geology itself. We are betting that we can engineer our way out of a physics problem. But the sinking land of Arizona stands as a testament to the fact that nature always bats last. The water is gone, the rock is crushed, and the desert is reclaiming its space, 1 inch at a time. The silence of the sinking is not a sign of peace. It is the holding of breath before the collapse. We are learning too late that the most dangerous disasters are the ones you never hear coming. We are standing on a hollow world, and we are the ones who hollowed it out. The question now is not if the ground will stop sinking, but how low we are willing to go before we stop digging.